Hey class, in this episode we're going to be looking at deriving units. We're going to figure out what that means to derive a unit. It's a very fundamental basic concept in physics and sciences, any kind of science really, but physics, chemistry, especially physics, things where disciplines where you're using a lot of math, a lot of equations and a lot of analysis of variables, deriving units. This is a skill set that you're going to want to master, and you already know how to do this. Just the concept of thinking about it this way might be foreign to some of you, just because you're just so used to doing rudimentary, just basic algorithmic type processes, but you don't really think about what it means. Deriving units helps you think about what it means and how to use it, what to do with it. So let's just get started, and I'm going to explain some more. I'll see you after the video. So, what does it mean to actually derive a unit? What does that mean? So, when we're deriving units, essentially what we're doing is we're actually making a definition. We're defining something, and particularly what we're doing is we're defining variables. And so you're used to basic mathematical algebraic expressions with equations and variables. They of course change, that's why they're variables, but once you know the value for a variable, then it helps you to solve the relationship that is within the equation or the inequality, whatever the case might be. So what we really want to understand first is that that units are derived from a situation. So we derive a unit from a situation. So here's where what we do is we think about the situation. What is happening? All right. What is happening? All right, and with that said, we know that when if we're talking about math, because when we're talking about physics, we're talking math, then what we're doing is for us, what is happening, those are various factors that we're concerned with. All right, so what we do is we need to make good observations. All right, we need to make very good observations using our senses. So, what you see happening, remember, this is all qualitative stuff, and we're going to take that qualitative observation, we're going to take measurements, right? We're going to take measurements. And by taking these measurements, this gives us units, right? And then from our qualitative observations that we make, we begin to sort of piece together a process. What is actually happening? And in our minds and with our senses, we start thinking if something increases or decreases, what does that do with the value? What does that mean for what we observe? And we use all of this to basically come up with an equation. And from that equation, we can derive a unit of measurement for what is happening. So let's practice. Let's go with something that is very basic, something that you're very, very familiar with. Okay, this is nothing new. You've seen all this before. You've seen velocity in basic math class. You tend to just talk about velocity as speed. We'll have another lesson where we make the distinction between speed and velocity. But for now, you just know that in math class they tend to they're measured the same. There's just one distinct difference, which is very, very important in physics. But for the speed equation, you basically have distance divided by time, right? And so in math class, it tends to be written S equals d over t. And if you've ever taken physical science, you tend to see velocity equals distance over time. And so both of these are the exact same equation. So we see here there is time. So what I've done is I've said, well, let's take the unit of time and let's derive that. So when we talk about derive, that means where it's from. where it comes from. So if you think back to maybe you had probably like a biology course, and when you talked about genetics, you talk about derived units, and in that sense, it means the same thing. It means, like for instance, you derive your characteristics, your eye color, your height, your hair color, things of that nature. You derive those characteristics from your parents, so they come from your parents, right? So that's all that means. So what we want to do is where does the unit of time come from in this equation right here? That's what we want to know. All right. So we've got velocity equals distance divided by time. So when we derive an equation, when we derive a unit from an equation, we don't need any values. We don't need any measurements. All we're doing is what you learned in your basic pre-algebra or your algebra 1. We are basically manipulating letters in the equations following the 4 math functions: multiplication, division, addition, and subtraction, whatever the equation has. All right, so here is the original form of the equation. So to derive means we want to show where it comes from. So if you were in your math class, so if you were in your math class, right? Then what you would do is you would go and you would multiply. You would only get time by itself, so you would multiply this side by t, right? And you can see that it would cancel out here, but you would also have to multiply this side by time, and you see that it does not cancel out. So now we have a new form of the equation: distance equals time, or actually, so distance equals velocity times time, right? So that is, I mean, it doesn't matter which way we write it, but if we read it this way, distance is equal to velocity times time. So I'm just rewriting it so we can read it from left to right, just like your math teachers taught you. Now we still we're trying to derive the unit for time, so time needs to be by itself. So we know that what we would do is we would divide this side by v, but we would have to do the same here because it's an equation. So now what we do is we have time equals distance divided by velocity. All right, and if we had actual measurements, we could plug them into this equation and we would have a value and a number. But every single time, what we would be doing is solving this equation without letters, which is just solving for the unit. So distance, we know, typically is measured in meters. That's going to be our standard measurement. And then velocity. Well, let's think about this for a second. What's the unit for velocity? Well, let's go back to this original equation. Velocity equals distance divided by time. Well, velocity, if we're going to derive the unit, distance is meters. Time, the universal measurement, is seconds. So that is the unit of measurement for velocity. So I'm going to come down here and I'm going to put meters per second here. Now, this literally goes back to before you ever learned algebra. You learned how to do your 4 basic functions with a fraction. This is a fraction. This is the same as meters divided by meters per second. And you also learned that whenever you have your functions written in this form, that you then multiply by your reciprocal. And so now you should see that meters cancels out, and you are left with just the unit seconds, which is the unit of measurement for time. This whole thing here, all of what we've just done here, that is us deriving the unit for time. It's very elementary, it's very simple, it's very basic, but this is a skill we're going to find is going to serve us time and time again. As we progress through a physics course, we're going to find that our equations become more and more complex, where we have multiple equations that are embedded together into one equation, one larger equation, which means we start having multiple derived units interacting together. And so if your algebra skills, if your skills with manipulating variables across an equation are a little rusty, this is going to help you with that. All right, taking a look at another example here. Acceleration. So remember, derive means where does it come from? So let's think about this for a second. If you're in a car and you are accelerating, you press on the accelerator, we tend to just call it the gas pedal, but it's the accelerator, right? And so it means it changes your speed. So let's think about this. We've got acceleration, and the variable is a lowercase a. So let's think about this. What is acceleration equal to? Well, if you're in a car or you're on a bicycle, something happens where you change your speed, and speed being velocity, for just the basic concept right now. And then if you think about it, you can measure your time and say, hey, when I sped up for about 7 seconds, or I sped up for about another minute, or you know that in your mind, for a certain amount of time, you changed how fast you were going. And so mathematically, what that means is you changed your velocity per some amount of time that you changed, that changed as well. So here's the basic equation for acceleration. Okay, this is the basic equation for it. So now from this, we're going to derive the unit for acceleration. So we just do what we've been doing all day long, or in this lesson. So acceleration equals the change of velocity over the change in time. Well, we learned in the previous part that velocity, meters per second, correct? All right, so right here, we know that our unit of measurement is meters per second. It's going to be divided by, we know that time is seconds. So now let's think about this. We've got meters per second divided by seconds. And as we've already discussed previously, whenever you have your functions written out this way, you always multiply by the reciprocal. So that would be 1 over s, because there's really a 1 over this, correct? So now let's think about this. Meters times 1 is meters. Seconds times seconds would be seconds squared. So anytime you solve for acceleration, you know you're doing your work correctly if, for solving for acceleration, you wind up with a unit that is meters per second squared. Every single time, that's what it should be. So it doesn't matter. We just solved basically an acceleration equation without actually plugging in numbers. That's all deriving means, is figure out something without using any values. We basically use the value 1 everywhere. So let's think about this. If I go acceleration equals a value of 1 here over a value of 1 here, well, 1 divided by 1 is going to be 1. Well, if all of a sudden now I put this here and this here, now you see that the rest of this shows up as well. So I would have 1 meter per second over 1 second equals 1 meter per second squared. All right, basic math. All right, let's take a look at something else. Usually before high school, you have some units in some middle school stuff, maybe a physical science or an earth science, where they talk about force, right? Talk about Newton's laws, right? And Newton's laws, pretty straightforward stuff. We'll be talking about that a whole lot in this class. But let me remind you, force you learned was mass times acceleration. And if you think about it, so if you force something, so if when you force something, you have to push or pull on it. So there's a box here. And if you push on this thing this way, then it moves from here to there. Well, if you think about it, this box has mass, which we measure using the unit kilogram. And then as this thing moved from here to there, so think of this as a floor. If you think about it, there was a certain distance, so we would always go from the center point to the center point. So if you think about it, there was a distance that it moved. And we could measure how much time it took to go from here to here. So that would be a change in time, right? Well, it's not going to basically be the same. It's changing its speed. First it was starting here and it wasn't moving, and then it went to here, right? Well, we've already talked about in a previous screen that when something is changing its speed, we're talking about acceleration. When something changes speed over time, that is acceleration. So we already know that the unit for acceleration is meters per second squared. Two variable letters next to each other means that you multiply them. So now we know that force is essentially equal to kilogram meters per second squared. That is the unit for force. And then you learned in your previous, like physical science, whatever the case may be, that we have a shorthand notation for this, which is just capital N, which we call a Newton. So both this and this are the exact same unit. Okay? So now we've derived the unit for force from the force equation. All right? Now, right here, this says derive the unit for acceleration from this. All right? So now, oops. So now that we have this here, all right? Now that we have this here, let's think about this for a second. So what I just did first was show you here's everything we need to know about force, and there's the unit for force. Well, let's rearrange this equation here. All right, let's start new. So if force equals mass times acceleration, well, we just do what our math teachers have taught us. We need to get acceleration by itself, which means I multiply this side by or divide this side by mass, and I divide this side by the mass. So now I have acceleration equals force divided by mass. Okay. So now, with this said, force we know is a Newton over meters, and we know a Newton is kilogram meters per second squared divided by the mass, right? Well, this is kilogram meters per second squared divided by the mass, correct? So now we know that this would be kilogram meters per second squared times the reciprocal, correct? And the unit for mass we know is kilogram. So let's think about it. I can go back here. I can oops. I can erase this right here, and I can make this a kilogram, correct? Which means if you think, I had technical difficulties for a second, I had trouble thinking about what I was doing. So if we know that this is mass as well, this is mass, then that means if you think about it, we can go back and we could replace that with kilograms. And then if you think about it, we also have this right here with kilograms. So now notice kilograms crosses out, and we're left with meters per second squared. We've derived the unit for acceleration from the acceleration equation. And actually that form of the equation we're going to find is very much related to one of Newton's laws, that form right there. We tend to think F equals ma, but that form that I just circled is actually more in line with one of his laws, and we'll discuss that in another unit. So I hope that's kind of helping you out a little bit. Let's apply this. Let's do something with this that makes it a little useful. All right. So we've got an object here. I don't care what it is. It can be a rock. It can be a bouncing ball. It doesn't matter. But it moves with an average acceleration. All right. So it's accelerating at 1.5 meters per second squared. When you see that unit, oh, and that should be a superscript. I just forgot to do that. I apologize. All right, at a rate of 6 meters per second. Well, we know 6 meters per second. When we see meters per second, we know that it has to be velocity. We learned that previously. So 6 meters per second. How long does it take? That must be time. All right. So here is everything we're given, and I will always expect you to write out what is given. Okay. All your givens, I expect to see those written out, and you're going to find that's going to save you a lot of headache and a lot of work later on. So we know that acceleration equals a change in velocity divided by a change in time. We want to solve for time, so what we have to do is essentially multiply this side by delta t and multiply this side by delta t, and now we see that we have delta v equals acceleration times a change in time. And now we still need to isolate time by itself, so we're going to multiply this, we're going to divide this side by acceleration, and do the same over here. Okay. So now we've got delta t, our time variable, is equal to the change in velocity over that object's acceleration. So now this is the new form of the equation to solve for our variable. We've isolated the unknown in what we're solving for. This is a process that you have to do with every single thing that we do in class. Okay. So now let's think about this. I've shown you before how we were just deriving units. Now we're just solving it. Well, we know what delta v is. All right, change in velocity is 6 meters per second divided by the acceleration, which is 1.5 meters per second squared. Okay, not a problem. So we've got 6. This is the easy thing to do here is what we always do, and I'll be honest with you, what I'm about to show you, I don't spend time doing this myself, but we're going to find this, but this is going to be highly important in how we're going to need to do things for physics, because everything's just going to get more and more complicated. 6 divided by 1.5 is 4. There's nothing difficult about that. So the question is well, we're solving for time, so we should just have seconds left, right? So I'm just going to write seconds. But the problem is that between here and here, there's no work shown on exactly what was done to get 4 seconds and what happened to every other variable there. Because if you think about it, there's 1, 2, 3 units of seconds and 2 units of distance in this. But now there's only one variable left over at the end, which in this case, that variable is the unit. So what we have to do is we have to show the whole process. So I'm going to come below this. Delta t equals delta v over the acceleration. Well, we already know that this is 6 meters per second divided by the acceleration is 1.5 meters per second squared. That is 6 meters, excuse me. Sometimes I write too quickly, and so I'll try to slow myself down. 6 meters per second divided by, and that is 1.5 meters per second squared. Now there is our division line. So we know that just like we've done before, we've got 6 meters per second times the reciprocal. There's a 1 down here, so that's second squared over 1.5 meters. Now we notice that seconds, but there's 1 left over. Meters over meters cancels out. You should be able to now see that what this is 6 divided by 1.5, which is 4.0, and the only unit left is seconds, and it's on the top. 4 seconds. All right. So all of this in between that we just did right here, I know that that is not difficult to do, but we're going to find that what we're going to be doing later in in this course is going to get just more and more complex. There's going to be a lot more steps involved, and if you cut corners, you're going to find that you're going to get stuck more often than you want to, and so I'm trying to help you avoid that. All right, so there's a practice problem with that, and we're going to have plenty more. You've got problem sets to be working on. You can always refer back to this. We've taken a look at force, we've taken a look at acceleration, we've taken a look at velocity, just the basic concepts of what a derived unit is. I hope this helped. I'll see you in class. Bye. And there you have it, deriving units. Please rewind the video, go to the different markers that I have for you, the different timestamps, and look at this over and over again. This is a skill set that is going to serve you well in this class, and it's really going to help you learn how to get some very logical way of thinking, how to sort of step back and look at something and then really think about how all the pieces come together. You should have seen that from what we've just talked about in this video, and it was very basic stuff. These are equations and things that you've always been familiar with, but this is a skill set that is going to serve for whether or not it's a small equation like what we were working with, or these really huge equations that have multiple variables where we're using derived units within an equation to derive a singular unit, which is a multiple of derived units. So with that said, hopefully this helped. Tune in for the next video, and good luck. Practice. It was good seeing you. Bye.